Next speaker, that is Carlo Lovadina. Carlo.
Can I share the screen?
Yes, you should.
Okay.
Be okay.
Can you see my screen?
Yes, if you want to put it in full screen. Okay, this is
be okay, right? Okay.
So Carlo will speak about, of course, virtual element method, and in particular for the about the Hellinger-Reissner variational principle. So, please.
Okay, thank you, Stefano, and many thanks to all the organizers for the invitation to speak here in this workshop. I would like to highlight that this is a joint work with several people, and the people are just shown here. They are Edoardo Ortioli from Roma, Franco Dassi and Michele Visinoni from Milano Bicocca, and then from Bologna, Stefano De Miranda and Luca Patruno. So I will talk about virtual element methods for elasticity problems, and in particular, I will use the mixed form of the elasticity problem. Just my setting is the easiest one, which means that I'm considering infinitesimal elasticity and also linear elasticity for what concerns the constitutive law. So here you recognize the typical problem of the elasticity. So you have the equilibrium equation, then you there are the stress that is involved, and the stress here is symmetric, so it's a symmetric field. And then you recognize here the constitutive law, in which also the displacement field comes into play. And then there are the boundary conditions that here are considered as homogeneous. So the problem, of course, is to find out stresses and displacements. And, you know, since we are going to employ a Galerkin method, this problem must be written in variational form, and I will use the standard Hellinger-Reissner variational form that I'm sure that you are familiar with. So the problem, I'm also using, I would say, standard notation to describe the problem. So here we have the constitutive law equation in a variational form, and this is just the equilibrium equation also in variational form. And say the spaces involved in such a formulation are the H-div with made up of symmetric tensors, sigma, and then there's the L2 space for each component of the displacement field. Okay, and then the bilinear form here, A of sigma tau is basically the L2 product, and then there's the material coefficients here. So D is just the inverse of the C tensor, which is a symmetric fourth order tensor. Okay, so I would like to point out that this space H-div with symmetric condition for the stresses means basically that in coming from an element to the adjacent one, then the tractions, so the normal component of the stresses are continuous. Okay. Okay, so it's pretty well known that if you go to finite element methods and you want to say find a conforming approximation of such a problem, so the Hellinger-Reissner formulation, then you have to fight against three conditions that altogether are very hard to satisfy. So this means that if you would like to insist that your finite element method must have a symmetric tensor for stresses, must be a local polynomial, and must have an H-div conformity, well, it's not easy to find the method. Okay, of course there are alternatives. The first alternative can be to reduce the symmetry. So you don't want all the properties to be satisfied, and then you relax the first one, for instance, and then you may think of considering the Pia's element of Arnold, Bretzi, and Douglas. But you can also try to say get rid of the local polynomial approximation, which is typical of finite element methods. And the possibility here is just to consider composite elements, Unson-Mercier element, for instance. You may get rid of the conformity, the HDIV conformity, and of course there are the discontinuous Galerkin approach here that can be considered. And well, to tell the truth, there are alternatives also satisfying the three properties, and then you come up with the Arnold-Winter element, for instance, in which, however, you have for the stress field, you have nodal degrees of freedom. Then we will see that this can be a kind of drawback in a sense. Anyway, the Arnold-Winter element, which is a conforming element with the symmetric stress, has this diagram, I would say. So, I mean, it's there are 30 degrees of freedom locally in the triangle. It's a triangular version here, 2D. Okay, so it's not exactly very easy, I would say. So now the idea is just to use the VEM approach in order to design something using the Hellinger-Reissner formulation for the elasticity. And more precisely, the idea is to try to exploit the flexibility of the virtual elements in order to design something for which the stresses are ab initio symmetric. The scheme, the method has the natural conformity, so it's HDIV conforming, and possibly you will not have degrees of freedom at the vertices of the polygons in such a way that it is possible to hybridize the problem. And with this respect, there will be soon a talk by Michele Visinoni. Okay, so let's see how to reach this goal. Of course, the first step is just to write down the discrete variational formulation. So this means that you have to choose, well, you have to consider the problem, and then you restrict the problem to discrete spaces, virtual spaces. In this case, it's just sigma h, which should be contained in HDIV, and UH that should be contained in L2, but this is not a problem, of course. And then after that, you have to define the approximated bilinear form AH, which should mimic the original bilinear form A, which is more or less the L2 product in L2 product between tensors. Okay. And in our VEM discretization that I will detail very soon, I would like to remark that this mixed term here, as well as the loading term here, are not modified. This is just a consequence of the choices that we will do for sigma h and UH. Okay, so you have to modify only this part here. Of course, provided that you have a good numerical rule, numerical integration rule for polygons or polyhedral. Okay, in 3D. I would like to tell you that actually we don't have a single element, but we have a whole family, and the whole family can be described as follows. There's a lowest order case for which we have also a three-dimensional version. and this element will be denoted with k1/2. And for k which is greater than 1, we have a whole family which basically have the same structure. So in this talk, I would like to focus on the two-dimensional case and also to the lowest order case, just to show you which is the idea of the design of such elements. So as I've already told you, we have a three-dimensional version out of it, and this lowest order case is made up by a choice for which the displacements are in between the piecewise constant functions and piecewise linear function. That's why I would say k is equal to 1/2 is the notation we used. And also for the local stress space, as we will see in a moment, we have that the stresses contains the piecewise constant functions on the mesh. Okay, so let's detail a little bit the local virtual spaces that we are employing in such an element. For the displacements, we will use the not the piecewise constant function, but this space here, which is nothing but the rigid body motions on each element on each polygon. Okay, so you have a constant part, and then you have this guy here, which basically is just an infinitesimal rotation around the center of the polygon here. Okay, so this of course has dimension 3 in each element and contains constant, but it is not full P1 polynomials. Okay, we will come back to this choice later on. So of course, this is not very virtual. I mean, it's just polynomial space. So the virtual element method comes into play exactly in the selection of the stress space, because in each element, what we will do is just to solve a pure traction, so to say, elasticity problem, and then we extract the stresses. And the elasticity problem that we want to solve has a particular set of data. The tractions are in such a space, which means that on each edge of the element, there's a tangential part which is constant, and then there's a P1, the normal part is just P1. So it's just constant along the tangent direction, and it's P1 along the normal direction. This is just the traction we are imposing to define this guy here. And then we said that the divergence is exactly in the rigid body motions of the element. Okay, so the set of data are exactly the tractions on each edge, and then we define where the divergence of such stresses lives. And just a remark about this choice, and the remark is that if you know the tractions on the boundary, in particular on each edge of the element boundary, well, then the divergence is completely determined. And this is, of course, a consequence of integration by parts formula, because if you consider this guy here, in which you test your divergence, which is in the Rm space with the test function, which is again in the rigid body motions, and then you integrate by part, then due to the symmetry of tau h, then you see in integrating by parts only the symmetric part of the gradient of R, which is 0, and then everything that you see is just on the boundary. Okay. And here you may see the explicit description of the divergence once you know that the tractions are given by the parameters CE and DE on each edge. Okay, so of course this has a consequence, and the consequence is that in this space, actually, this fact does not contribute in the dimension of the space. Put in other words, the dimension of this space is given by 3 times the number of edges of your polygon, and it is dictated exactly by the boundary values of the normal part of the stresses. Okay. So one may wonder why not choosing, say, probably more natural spaces here, for instance, in the divergence. Why do you choose this rigid body motion instead of, for instance, constants? And so piecewise constants, if you consider the mesh, again, the answer is integration by part formula, because you know, whatever you choose for the divergence, this formula tells you that the projection, so the rigid body part of your divergence, is completely determined by the boundary. The boundary tractions, okay? So if you now insist that the divergence, instead of being in the rigid body, is in the constant, in the element, then this introduces a constraint here in the element, which immediately diffuses to the boundary and introduces a sort of unwanted constraint for the tractions, because you know the traction, you should have tractions which are say local, which should be local on each edge. I mean that if you have such a constraint which is not local, then it is not very easy to glue together contributions in order to meet the H-diff conformity. Okay, so this fact of insisting to be piecewise constant is, so to say, not very compatible with the traction here. Okay, and even if you choose, say, constant tractions on each edge, this does not solve the problem. Okay, you get into trouble again. So that's why we have chosen probably at the first sight a sort of bizarre space for the divergence of the stress here. And of course, this has a consequence also on the choice of the displacement field, because if you reduce the displacement field, then you are in trouble for stability reasons. And in particular, you are risking the coercivity on the kernel condition at the discrete level. So this fact, so to say, justify the fact that the displacements are in Rm, and the stress space is given by the sigma h I've just described. So for instance, for a pentagon, this is just the schematic description of your element. You have 3 degrees of freedom for each edge here, corresponding to the space Re that I've introduced before, and this is just the 3 degrees of freedom for the displacement field UH. Okay, so once you have the the virtual spaces described, then we can pass to consider the approximation of the bilinear form A, which is done in a pretty standard way. So this means that you first need to introduce a projection operator onto, in this case, onto constant functions. So I would say the Hellinger-Reissner version of the pi nabla operator in the framework of the Laplacian problem. Okay, but this is done in a pretty standard way. And it is possible to prove that this is actually computable, of course. And then once you have the projection operator onto the piecewise constant functions, tensor functions, symmetric tensor functions, then you say define everything as usual. So the local discrete bilinear form is just the sum of two contributions. The first one is just the consistent part, and then there's the stabilization, which in this case can be this form here, in which you just weight the L2 product along the boundary of each element of the tractions, basically. Okay. Here, this constant kappa e, you may take, for instance, the trace of the D tensor. Okay, so this perfectly works. So this is just a part which is pretty standard. It's just the say the L2 version of the pi nabla operator. Okay, so in doing that, I would like to remark that we have that the discrete tractions may be discontinuous at the vertices of the polygons. So we don't have sort of any continuity just in the vertices. Okay, so the stresses are just built symmetric a priori. And if you compare, say, the Arnold-Winter element for triangles with our VEM element for triangle, well, there is a reduction in the local degrees of freedom. We have 12 instead of 30. Okay? So for such an element, it is possible to derive an error analysis, a stability and error analysis, and what you obtain is something that you expect, and this means basically that your element is a first-order convergent, provided, of course, that the solution is sufficiently regular. Okay, the method is, as all the, I would say, all the methods based on the Hellinger-Reissner formulation, the error bound and the method is robust with respect to the incompressible limit. So you can use it also for rubber, for instance. Okay, so let us come quickly to some numerical tests. These are just the mesh adopted in 2D. We have considered a couple of problems, and here you see, say, the convergence history of the method, and everything is good. Okay, also for test B, also for the incompressible test case, there's nothing bad, I would say. And as I mentioned before, we have a whole family, so we have high order schemes that you can design. These are done in 2D, but Michele Visinoni is working also on the extension on the 3D case. Okay, so we expect that quite soon we have 3D versions out of them. Okay, so this is just the schematic description of the case k is equal to 1. We have a theoretical analysis out of it, so the right order of convergence, again, robustness with respect to the incompressible limit. And again, here we have performed numerical tests confirming the theoretical results. Just a few words about the 3D case. For the lowest order case, we have a 3D version, as I mentioned before, of our method. Basically, the stresses and the displacements are designed using the same philosophy. Here, I've just written down the spaces, and I would like only to remark that on tetrahedra, our VEM element has locally 30 degrees of freedom, while if you go to a 3D version for VEM, well, you have quite a lot of degrees of freedom, locally speaking. Okay, so we have performed numerical tests and on such meshes, and everything went pretty okay. So I'm coming quickly to conclusions. We have designed, analyzed, and numerically tested some virtual element methods using the Hellinger-Reissner functional. And the main features of such methods are that the stresses are symmetric, a priori symmetric. The methods are robust with respect to the incompressibility limit. It is possible to easily design high-order methods and also 3D schemes, and they can be easily hybridized, since there's no nodal degrees of freedom for our methods. So for me, it's all, and I would like to thank you for your attention.